Good morning, 8th grade. We're going to go ahead and get started on the next chapter, which is chapter 6. Since we're starting a brand new chapter, I'm on the next blank page of my notebook, and I'm going to write chapter 6. Just like that. Alright, then I'm going to flip to the next blank page, and at the very top, I'm going to write chapter 6, and we are on section 1. And today we're going to be talking about something called systems. Oops, I missed a word. Sorry. Solving systems. It goes in there. Solving systems by graphing. We're going to talk about what systems means and how we solve them by graphing. So before we get started, we're going to have a little bit of vocab. Oh, I think my pen's running out. Hold on. I'll be right back. Never mind. It's okay. There we go. There we go. Now it's back to working. Okay, perfect. All right, so first, before we actually start solving what a system is, we need to talk about what is a system. So when I say system, the full expression is system of equations. So just know if I say system, I mean this entire thing. So a system of equations is two or more linear equations. Okay? And if we're talking about the solution of a system of equations, that is where all of these linear equations meet, where all meet or intersect. And the solution is going to make all of the linear equations in that system true. Makes all equations true. Meaning, if my solution works for one of them and it works for the other, that is the solution for both of them. Both equations will have multiple solutions, but there might only be one that works for both. Alright, so we are going to go ahead and get started on this. I'm going to put a number 1. And if you have some graph paper near you, I have some over here. That's great because we are going to be using it today. If you don't, that's okay. Just draw a coordinate plane and go from there. Alright, so you should have gotten a couple cutouts that I posted on the Google Classroom. If you did not cut them out yet, please pause the video and do so. This should be, hang on a sec, the first one. Oh, not that one actually. Hang on, this one. That's the first one that we're going to glue in. So I'm going to put a letter A. I'm going to glue this in, and I will be right back. Alright, so mine is glued in. As you can see, we've got two equations off to the side here, y equals x plus 2 and y equals 3x minus 2. Now, one of the ways that we can solve systems is by graphing them. We can put them both on the same coordinate plane and see where they intersect. So, I'm going to go ahead and do that. I've got my graph paper, and I'm just going to put 6-1 off to the side here so that I know these graphs go with 6-1, and I'm going to put 1A. Alright, and I'm going to draw this kind of big like that, and put this one like that. Hopefully that's enough room. I always end up making them too small in one direction or another. Okay. So the first one was y equals x plus 2. So we're going to go ahead and graph this. We're going to start at the y-intercept, which is positive 2. And the slope, even though there's nothing in front of this x, I know that it's a 1 because there's always a 1 in front of a variable. So I'm going to go up 1 over 1, up 1 over 1, over 1, over 1, and continue like that. And I'm also going to put some beneath as well, because I'm not quite sure yet where these are going to intersect with each other. Oh, I smudged everywhere. Oh, well. All right, and connect There we go. Okay. All right, so that is my y equals x plus 2. I'm just going to label it so I remember which one I've done so far. My other equation was, there we go, y equals 3x minus 2. So I'm going to start at the y-intercept, which is negative 2, and the slope is a positive 3. So rise over run, I do up 3, 1, 2, 3. Wait, 1, 2, 3, yep, over 1. 1, 2, 3, over 1. That looks like my intersection there. I'm just going to plot a couple more points. 1, 2, 3, over 1, and that should do it. Okay. Ooh, that's a nice straight line. Look at that. All right, so that was my y equals 3x minus 2. And they intersect here, which is at 2, 4. So this one solution makes both of these true. Now, we know that these lines have infinitely many solutions. Anything along this line would make this one true. Anything along this line would make that one true. But there's only one that makes both of them true. But what I'm going to do is just double check that this works. How do I do that? I'm going to pop back over here into my notebook. I found that the solution, at least I think so, is 2, 4. And what I'm going to do is plug these in to each of these equations and see if it makes sense. So I have y equals x plus 2. So instead of y and x, I'm going to put the values I had. 4 equals 2 plus 2. 4 equals 4. Yep, that works. So we're good there. Let's check this one. Y equals 3x minus 2. 4 equals 3 times 2 minus 2. 4 equals 6 minus 2. 4 is 4. Yep. So I know that this solution, or this is the solution for both of those equations. Let's try another one. I'm going to go down here, write a letter B, and the next cutout I have looks like this. So we're going to go ahead, paste that in, and then continue. Alright, mine is glued in. So, we're actually using one of the lines that we had from the previous one, y equals x plus 2, and we're adding in this new one, y equals 2x plus 4. So we're going to see where do these two lines intersect with each other. Now, I'm actually going to use, oh wait, you know what? I'm going to grab some highlighters. Be right back. Okay, I'm back. So, since I already plotted that line, I'm just going to go ahead and use the same coordinate plane that I did for the other one, but I'm going to incorporate some highlighters this time. So I'm going to highlight this guy in yellow, and I'm going to highlight my other one in pink. Alright, so I'm just going to use this one that I had from last time. Alright, here is y equals x plus 2. Alright, I'm going to ignore this guy for right now. And I'm going to now be putting in y equals, what was it? 2x plus 4. And I'm going to highlight him in pink once I have him graphed. Okay, so we're going to start at the y-intercept. 1, 2, 3, 4, right there. And the slope is 2, so I'm going to go up 2 over 1, up 2 over 1. Might have to go lower. You know what? I think I might. I'm going to plot some beneath as well. Up 2 over 1, up 2, ooh, I'm getting a little high here. Up 2 over 1. I think these are going to have to meet a little higher, so I'm actually going to extend my other line. Let me get a straight edge. Be right back. Hey, I'm back. I realized I was just looking at the wrong line. The yellow one that I actually highlighted is the one that I'm supposed to be looking at. Okay. Let me go ahead and plot some more points for here because I think it's going to be lower. Down 2 over 1, down 2 over 1. There it is. Got it. Down 2 over 1. Okay. Now let me use my straight edge. Connect to these points. I didn't even have to go higher. I was just looking at the wrong line. There we go. There we go. Okay. So that is my pink line. And that one was y equals 2x plus 4. There we go. Alrighty. So, we can see that they intersect right here, which is at -2, 0. But let's just make sure that that solution works. So I'm going to go back over to my notebook. We had -2, 0. And let's make sure that this is true. So I had y equals x plus 2. 0 equals -2 plus 2. Yep, that one works. So that one is true. Now we have y equals 2x plus 4. So 0 equals 2 times -2 plus 4. 0 equals -4 plus 4. Yep, that one works too. So I know that -2, 0 is the solution to these two equations. All right, so we are going to continue, but this time we're going to be writing a system of equations. So I'm going to put a number 2. And the next cutout you should have should look like this. So go ahead and paste that in, and I will do the same. Alright, so I have mine glued in. I'm going to get started. We are going to be writing equations for both of these, I guess, alligators, and then we are going to see where they intersect. And I'm going to show you what words in this, let me adjust that a bit, there we go. What words in this word problem tell me to find where they intersect. So it says, scientists studied the weights of 2 alligators over a period of 12 months. The initial weight and growth of each alligator is shown below, here and here. After how many months did the alligators weigh the same amount? All right, that key phrase, same amount, tells me I want to see where they intersect. What combination of weight and months is going to make it true for both alligator 1 and alligator 2? Now, before we do that, we want to figure out equations for both of these guys. So I'm going to use the variables W. W is going to be their weight in pounds. And I will use M for the number of months. Okay. I'm actually going to ignore this 12 months up here. This just tells me how long they were collecting their data. It doesn't really, it's not going to be incorporated into my equations. So this is just how long they were doing it. Alright, so let's do alligator 1. The first guy, his weight, W, is going to be, well, he started at 4, and he gained 1.5 pounds per month. So that is my first equation. And you know what? I'm going to rewrite this in just a second. I'm going to show you why. The next one, so this is alligator 2, his weight started at 6, but he only gained 1 pound per month. Now I'm actually going to rewrite this because I am going to have to graph it. And when I graph, I prefer fractions. So instead of 1.5 m, I'm going to write it as 3/2 m plus 4. These represent the same number, it's just going to be a little bit easier to graph that. And I'm just going to rewrite this as m plus 6. Because I know that 1m and m, they represent the same thing. So I'm going to go ahead back to my, oops, dropped something. I'm going to go ahead back to my graph paper. Okay? And you know what? I'm actually going to use highlighters again. Let me get the one I dropped on the floor. Got it. Okay. Alright. So this is number 2. I'm just going to put a 2 there. And do that. Do-do-do. Do-do-do. And do-do-do. Do-do-do. Okay. There we go. So, let's go ahead and start with alligator number 1. That was the 3/2 m plus 4. Alright, so W equals 3/2 m plus 4. Alright, I'm going to do him in pink. 1, 2, 3. Okay. So we're going to start at 4. 1, 2, 3, 4. And up 1, 2, 3 over 2. 1, 2, 3 over 1, 2. And I'll do some beneath as well. 1, 2, 3, 1, 2. 1, 2, 3, 1, 2. That should do it. Alright. Let's go ahead and connect the dots. There we go. Definitely better with the straight edge. Okay. And that is my pink line. There we go. Alright, now let's go ahead and do my other guy. The other one was W equals M plus 6. So we're going to start at 6. So this one was 4, 5, 6. Up 1 over 1, up 1 over 1, up 1 over 1, up 1 over 1. Found it! Let's go ahead and connect those. Oh, I forgot. Let's highlight him in yellow. There we go. And connect my dots. There we go. Alrighty. So, if you remember, my M stood for number of months. That's what we plotted along the x-axis. And the y-axis was the weight in pounds. So if this was 1, 2, 3, 4, 5, 6 months, then this was up by 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 pounds. Alright, so it looks like at 4 months, they both weighed 10 pounds. Let's just check and see if that's true. So, 4 months, 10 pounds. We're going to plug these in, make sure they work. So, 10 equals 3 halves times 4 plus 4. 10 equals 6 plus 4. 10 equals 10. Yep, good to go there. Let's check for this guy. 10 equals 4 plus 6. Yep, that works. So at 4 months, both of these guys weighed 10 pounds. All right. We're going to move on to the next section. And we're going to see that not always do these equations behave the way you want them to. And I need to go grab some coffee, so I will be right back. Okay, I am back. So we are going to get started on the next part. And I've written a number 3, and we're going to put what is the solution. Alright, so let's start with this one. I'm going to write down 2 equations. We have 2y minus x equals 2, and y equals 1/2 x plus 1. Okay, so we are going to graph both of these. I'm going to start with this guy because he's already in y equals mx plus b form. And let me just get a new sheet of graph paper. I'm just going to use the back. Alright. So I'm going to draw this. Just like that. Okay. Just like that. And this is 3a. I'm just going to put that off in the corner. Alright, so the first one was y equals 1/2 x plus 1. I'm going to highlight him in yellow and graph him. Alright, so we're going to start at the y-intercept, which is positive 1. And we're going to go up 1 over 2, up 1 over 2, up 1 over 2, and I'll do some beneath as well. Down 1 over 2, down 1, 1, 2, 1, 2. Alright, let's connect our dots. Just like that. Alright, and that will be yellow. Okay. Now, before we can graph the other one, let's go ahead and put him into y equals mx plus b as well. So in order to do that, I need to move x to the other side. So I'm going to add x to both sides. I get 2y equals x plus 2. I divide by 2 on both sides, and I get y equals 1/2 x plus 1. So I ended up getting the exact same thing. If I was going to go ahead and graph that guy, so it originally started as 2y minus x plus, or equals 2. Okay, and if I did him in pink, I would end up getting the exact same line. It would go just like this one did, all of these points. And this would also be my pink line. So these two lines intersected. They completely overlap each other. So if you get something where the lines are the exact same, there isn't one solution, there aren't two solutions, there are infinitely many solutions. Infinitely many solutions. Because they are the exact same line. They're always going to overlap, so no matter what point you pick along those two lines, it's going to work for both of them. Let's try another one. Alright, I'm going to put a B. Let me flip my page in my other book. There we go. And let's write this. Y equals 2x plus 2. And y equals 2x minus 1. Now you might notice something right off the bat about these two equations. I notice the slopes are the same. So when I go to graph these, I'm going to go over here, put 3b. When I go to graph these guys, okay, got y equals 2x plus 2. So start at positive 2, up 2 over 1, 2 over 1, 2 over 1, and I'll plot some beneath as well. Okay, get my straight edge, and connect. Alright, I'll highlight him in pink. Actually, I don't know if it's a him or a her. It's an equation, it doesn't have a gender. The other one was y equals 2x minus 1. So we start at negative 1, up 2 over 1, up 2 over 1, up 2 over 1. I'll plot some beneath as well. Down 2 over 1, down 2 over 1. And I'll highlight him in, or it, the equation. I will highlight the equation in yellow. And connect my dots. Do 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 do. There we go. So here was my pink line and my yellow line. These lines are parallel. We actually knew that going into this because we saw that the slopes were the same. But these lines are parallel. That means they will never, ever, ever intersect. So, what is the solution for these two equations? There isn't one. No solution. There is nothing that will make both of these true. At least, you know, for both of them. No one solution that will make both of them true because they are never going to intersect. It will never, ever happen. Alright, so that being said, there's a couple more cutouts that we're going to put in. But before we get to that, few more vocab words. So we have equations that can be one of two things. We have equations that can be what we call inconsistent. Alright, that's this guy up here. There is no solution that's going to make them true. And there should be a cutout that looks something like this. So go ahead and glue that in underneath him. Alright, so this guy here is inconsistent. If a system of equations is inconsistent, means there's no solution that's going to make them true. Now, you can also have, and I'm just going to put a divider line, you can also have graphs that are consistent. That means there is at least one solution. Okay? So you should have two more cutouts. These should be the last ones. They should be these two guys. So go ahead and glue those in. Okay. So these two graphs have at least one solution. But you'll notice, and it's kind of hard to tell with this one, it's supposed to be two overlapping lines. If a system is consistent, it can be one of two kind of like subcategories. If you have only one solution, like this guy does here, this is called an independent and consistent system. So it's independent because there's only one solution, and it is also consistent because they do intersect at least one point. This one has infinitely many solutions because this is two overlapping lines. They're the same line, so this is what we call a dependent system, but it is also consistent because there is at least one solution. There's actually more than one, but there is at least one. Alright, so that is going to be the end of this section of notes. I'm going to have you hop on over to IXL and practice these skills there.